Look at the clock nearest to you. Whatever it reads, it agrees, with the clock in the next room, with the one at your work, with the atomic clocks disciplining every satellite overhead. That agreement is so reliable that nobody has ever thought to be grateful for it. It is also not a law of nature. 26,900 light-years away, in the direction of Sagittarius, sits a black hole weighing 4,297,000 suns, and its event horizon would fit inside the orbit of Mercury. Cross almost the whole distance to it and nothing happens at all. 1 light-year out, your watch still keeps pace with Earth's to a part in a million. Then, in the last few tens of millions of kilometres, all of it arrives at once. Tonight you will find out exactly what distorts as you approach the centre of our galaxy, and by the end you will know that the word distorts was doing something the entire time. Get cozy. If you are the kind of person who enjoys finding out that something you took for bedrock is only a local arrangement, a slow like and subscribe helps this channel reach more minds like yours. Because by the end of tonight, the agreement between your clock and everyone else's will stop looking like a fact about the universe. Now, let's slowly settle in. The galaxy has a centre, and we know its address. That sentence is worth sitting with for a moment, because it did not used to be true. For almost the whole history of human beings looking upward, the Milky Way was a band of light across the sky, with no obvious middle, no obvious edge, and no obvious anything. It took until the 1920s for us to be confident that we were not at the centre of it. It took until the 1970s to find the thing that is. And it took until quite recently to be able to say, with real precision and without hedging, exactly how far away that thing is and exactly how much it weighs. The direction is toward the constellation Sagittarius, low in the summer sky if you're in the northern hemisphere, high overhead if you're south of the equator. The distance is 8,277 parsecs, with an uncertainty of about 9 parsecs from the statistics and about 33 from the systematics. In the units most people are comfortable with, that is roughly 26,900 light-years, and the object sitting at that address has a mass of 4,297,000 times the mass of our Sun. Those two numbers are the foundation of everything that follows tonight, so it is worth being precise about where they came from. They were not estimated. They were not inferred from a model of how galaxies ought to be arranged. They were measured, over roughly 3 decades, by watching individual stars complete orbits around an object that emits almost no light at all. The mass is known to about 1%. The distance is known to about 4 parts in 1,000. For an object at the centre of a galaxy, 27,000 light-years away, behind enough dust to hide it completely from every optical telescope ever built, that is an extraordinary piece of work, and we will come back to how it was done. The object is called Sagittarius A star. It is a supermassive black hole, and the first thing to understand about it, before anything else, is how small it is. Here is the number. The Schwarzschild radius of Sagittarius A star, the radius of its event horizon, the surface from which nothing returns, is about 12.7 million kilometres. That makes the horizon roughly 25 million kilometres across. Now 25 million kilometres is a large distance by any human standard, but hold it against the things it is actually competing with. The Sun is 1,392,000 kilometres in diameter, so the horizon of the most massive object in our galaxy is about 18 times the width of our star. That is big. It is not remotely as big as you were expecting. And here is the comparison that ought to do the real work. Mercury orbits the Sun at an average distance of about 58 million kilometres. If you took Sagittarius A star and dropped it where the Sun is, its event horizon would not reach Mercury. It would fit inside the orbit of Mercury with room to spare. That is the thing at the centre of the Milky Way, a sphere 25 million kilometres wide. The galaxy it anchors is about 100,000 light-years across. If you work out the ratio, the width of the horizon against the width of the galaxy, you get something like 1 part in 35 billion. The object that defines the centre of everything we belong to occupies a volume that would be lost inside the inner solar system. There is a consequence of that size that most people find genuinely difficult to accept the first time they hear it. The formula for a Schwarzschild radius is linear in mass. Double the mass, double the radius. But volume grows as the cube of radius, which means that if you define a black hole's density as its mass divided by the volume enclosed by its horizon, that density falls as the square of the mass. Work it out for Sagittarius A star, and you get roughly 1 million kilograms per cubic meter. Dense, certainly, but not absurd. Work it out for the largest black holes we know of, the 10 billion solar mass monsters at the hearts of giant elliptical galaxies, and you get something less dense than water. Some of them are less dense than air. The most extreme gravitational objects in existence are, by that particular measure, remarkably thin. I want to be careful here, because this is the point at which the intuition most people carry starts to fail, and it fails in a way that will matter for the rest of the night. The phrase, the centre of the galaxy, tends to conjure something enormous. A zone. A region light years across, seething, dominating, unmistakable. That picture is wrong by a factor of tens of billions. The centre of the galaxy, in the sense of the object that holds the gravitational title, is a small thing in a big room. It is also, and this is stranger still, almost invisible. Supermassive black holes have a reputation as the brightest objects in the universe, and they have earned it. When one of them is feeding hard, the matter spiralling in gets compressed and heated and torn until it outshines every star in the galaxy that hosts it combined. Quasars are visible across billions of light years for exactly this reason. So you would expect ours to be a beacon. It is not. Sagittarius A star is radiating at something like 1/1000th of its Eddington limit, which is the theoretical maximum brightness an object of its mass can sustain. In practical terms, the supermassive black hole at the centre of our galaxy is outshone by a great many perfectly ordinary stars. It is starving. It draws in perhaps 100 millionth of a solar mass in a year, which for an object of its size is barely a rumour of a meal. And even that faint output does not reach us in visible light, because between here and there lies 27,000 light-years of the galactic disk, and that disk is full of dust. The dust imposes roughly 30 magnitudes of visual extinction along the line of sight to Sagittarius A star. 30 magnitudes is a dimming factor of about 1 trillion. Every single observation ever made of this object has been made in infrared, in radio waves, or in X-rays, because ordinary light simply does not survive the journey. Nobody has ever seen it. Nobody ever will, in the sense that you see the moon. So we have an object that is small, dim, buried behind dust, and holds about 3/10,000ths of 1% of the Milky Way's total mass. Everything about that description sounds like an anticlimax, which brings us to the question this whole video is built around. We're going to travel inward tonight, not physically. We're not going to spend the next 2 hours on rockets and fuel and how long the trip takes, because that is a different question, and it has different answers. Tonight the ship is granted. Assume you are on it. Assume it works. What I want to know, and what I think is genuinely one of the most interesting questions in physics, is this. On the way from here to there, at what point does reality stop behaving the way it behaves in the room you're sitting in right now? Because something does change. That much is not in dispute. The mathematics that describes the space around a 4 million solar mass object says quite plainly that the rules governing clocks and orbits and light and direction itself are not the same close to that object as they are out here. So there is a boundary, or a series of them. The question is where and how gradually and what exactly gets taken away at each step. And I want to flag something before we start, because it is the thing that makes this interesting rather than merely dramatic. The intuitive answer, that the distortion builds smoothly, that it gets a little stranger as you go, that reality thins out gradually the way the air thins out as you climb a mountain, is wrong. It is wrong in both directions at once. There are places on this journey where you would expect enormous effects and find absolutely none. And there is a place where essentially the entire effect arrives, all of it, in a stretch of the journey so short that after 27,000 light-years of nothing it feels like a trapdoor. There is also a second answer waiting at the end of this, underneath the first one, and it reverses the whole question. I am going to tell you now that it exists so that you know it is coming, and then I am not going to touch it again until the last part of this video, because it only works if you have made the whole journey first. By the end of tonight you will know exactly what distorts as you approach the centre of our galaxy. You will also know that the word distorts was doing something sneaky the entire time, and that once you see what it was doing, you cannot unsee it. So this is how we will travel, 12 steps inward. At each one, something you currently assume is simply a feature of existence, a permanent, universal, unremarkable fact about how things are, stops being available. Some of those losses are ordinary, some of them are not. We will begin at the beginning, which is here, 26,900 light-years out, in a quiet neighbourhood on a minor spiral arm, with a dark sky overhead and a clock on the wall that agrees with every other clock you have ever compared it to. And the first surprise is that for almost the entire trip, nothing happens at all. The quantity we are going to be tracking all night is a ratio. It is one of the simplest ideas in general relativity, and one of the hardest to make peace with. Take a clock and put it somewhere in a gravitational field. Take an identical clock and put it far away, where the field is weak. Let them both run. They will not agree. The one deeper in the field runs slower, not because it is broken, not because something is interfering with its mechanism, but because time itself passes at a different rate there. The ratio between those two rates is the thing we care about, and for a non-rotating mass it has a beautifully compact form. For a clock held stationary at some distance from the centre, the ratio is the square root of 1 minus the Schwarzschild radius divided by that distance. If the clock is not hovering but circling in orbit, its own motion contributes as well, and the expression becomes the square root of 1 minus 3/2 of the Schwarzschild radius divided by that distance. You do not need to hold those formulas in your head. You only need to notice one feature of them. They depend on the distance, and they depend on it in a very particular way. When the distance is large compared with the Schwarzschild radius, the fraction inside is tiny, and the square root of 1 minus a tiny number is very close to 1. The clocks agree. They agree almost perfectly, and almost perfectly turns out to cover an enormous amount of territory. Let us actually run the numbers for the journey we're taking. Start here, at 26,900 light-years. The ratio is 1 to more decimal places than any instrument could resolve. That is not surprising. But now move most of the way there, cross 26,000 of those light-years, arrive in the crowded central region of the galaxy, close enough that the sky above you has completely transformed, and stop at a distance of 1 light-year from Sagittarius A star. At 1 light-year out, your clock differs from a clock on Earth by roughly 1 part in a million. Sit with that. 1 light-year from a 4 million solar mass black hole, and the effect on the rate of time is a part in 10 to the 12th. Your watch and a watch back home would drift apart by a fraction of a second over a century. If you ran the experiment for the entire span of recorded human history, the two clocks would still agree to within about a minute, which means the following statement is true and is the opposite of what almost everyone assumes. The centre of the galaxy, considered as a region, has essentially no gravitational time dilation at all. Not a little, not a manageable amount, effectively none. You could live your whole life a light year from the object we are travelling toward and never once have cause to notice that relativity exists. Nothing has changed yet. I want to calibrate that against something you have actually experienced, because a part in 10 to the 12th sounds like a fancy way of saying 0, and it is not. It is a real quantity, and quantities of that size have been measured on Earth for decades. The clearest example is in your pocket. The global positioning system depends on a constellation of satellites each carrying an atomic clock, and those clocks do not keep the same time as clocks on the ground. Two effects pull in opposite directions. The satellites are 20,000 kilometres up, in a weaker gravitational field, so their clocks run fast, by about 45 microseconds a day. But they are also moving at about 4 kilometres per second, and motion slows clocks, so that takes back about 7 microseconds a day. The net effect is a gain of roughly 38 microseconds every day, and the system corrects for it continuously. If it did not, the positioning errors would accumulate at something like 10 kilometres per day. Every navigation fix anyone took today, in any car or on any phone anywhere on this planet, was computed using general relativity. It is not exotic physics. It is infrastructure. The effect has also been caught in far more direct ways. In 1959, Robert Pound and Glenn Rebka set up an experiment in a tower at Harvard, a tower 22.5 meters tall, which is to say a building, and measured the frequency shift of gamma rays travelling from the bottom to the top. The shift they were looking for was about 2 parts in 10 to the 15th. They found it. Time runs at measurably different rates between the ground floor and the roof of a university building. In 1971, Joseph Haefel and Richard Keating did something almost comically direct. They bought seats on scheduled commercial airline flights, put cesium atomic clocks in them, flew around the world eastward and then westward, brought the clocks home and compared them with clocks that had stayed on the ground. The eastward clocks had lost about 59 nanoseconds. The westward clocks had gained about 273. Both results sat inside the predicted range. The experiment cost about $8,000, most of it in airfare, and it is one of the cleanest confirmations of relativity ever performed, and the measurements have kept getting finer. In 2010, a group at the National Institute of Standards and Technology detected the difference in clock rate produced by raising one optical clock 33 centimetres above another, 33 centimetres, about the height of a stack of books. Then, in 2022, a group at Gila in Colorado resolved the gravitational redshift across a single millimetre inside a cloud of strontium atoms, 1 millimetre, roughly the thickness of a fingernail. The gradient of time is now something you can measure across the width of a coin, so the effect is real, it is verified, and it is everywhere. Here on the surface of the Earth, our clocks run slow relative to a clock far from any mass by about 7 parts in 10 billion, which works out to something like 22 milliseconds a year. On the surface of the Sun, the figure is about 2 parts in a million, around 67 seconds a year. And there is even a faint contribution from the galaxy itself. Sitting inside the Milky Way's gravitational well costs us something on the order of 1 part in a million relative to intergalactic space, which is perhaps half a minute a year. That last figure depends on which model of the galaxy's mass distribution you use, so treat it as an order of magnitude rather than a precise number. But the point stands, merely living in a galaxy is already, faintly, a relativistic condition. Now put all of that beside the number we started with. Everything in the last several minutes, the satellites, the tower, the airliners, the millimetre of strontium, lives in the range of parts per billion to parts per quadrillion. And when you travel 26,000 light-years toward the most massive object in our galaxy and stop 1 light-year short of it, you are still in that same range. You have crossed almost the entire distance, and the needle has barely moved. This is the fact I want you to carry into the rest of the video, because everything else depends on it. The curve is flat. It is flat for the overwhelming majority of the journey. 26,900 light-years of travel produce an effect you would need a laboratory to detect, and a curve that stays flat that long has to do something eventually. The mathematics is not optional. That square root does eventually plunge. It plunges because the fraction inside it stops being tiny, and the fraction stops being tiny only when the distance becomes comparable to 12.7 million kilometres. That distance is 12.7 million kilometres, out of 26,900 light-years, which is about 254 quadrillion kilometres. So here is the shape of what is coming. Essentially, the entire relativistic effect that this video is about, the whole of it, every part, is compressed into the last 100 millionth of 1% of the journey. Not spread out, not gradual, concentrated in a shell thinner than the orbit of Mercury at the end of a trip across a galaxy. But we are not there yet, and we are not going to skip ahead, because something else changes long before the physics does. It happens thousands of light-years before the clocks start disagreeing. It has nothing to do with relativity at all, and it is the first thing on this journey that you would actually notice with your own eyes. It is the sky. Our corner of the galaxy is close to empty. We do not experience it that way. Step outside on a clear night, away from streetlights, and the sky looks generously supplied. A few thousand stars visible to the unaided eye, the pale band of the Milky Way running overhead, the sense of a universe that is well stocked. But that impression comes from looking along enormous distances at very bright things. The actual density of stars around us is close to nothing. The standard figure for the solar neighbourhood is about 0.2 stars per cubic parsec. A parsec is 3¼ light-years, so a cubic parsec is a volume roughly 35 cubic light-years in size, and inside that volume you will typically find 1 star, sometimes not even that. Our nearest neighbour, Proxima Centauri, is 4.24 light-years away. In astronomical units, the distance from the Earth to the Sun, that is about 268,000. There is 250,000 times the width of Earth's orbit between us and the next star in any direction. We live at the bottom of an enormous empty well, and the sky we see is a long-distance view. Now travel inward. As you approach the galactic centre, the density climbs. It climbs slowly at first, then faster, and in the innermost region it climbs in a way that changes the character of the place completely. Within about a parsec of Sagittarius A star there is a structure astronomers call the nuclear star cluster, and its stellar number density is on the order of 10 million stars per cubic parsec. Detailed measurements of the inner profile find densities reaching around 10 to the 7th per cubic parsec, at a radius of 1/10 of a parsec. Set that beside our 0.2, and the contrast is roughly 50 million to 1. A ratio that large is hard to feel, so convert it into something with a scale you already own. Density and separation are related simply. If you have a certain number of objects per unit volume, the typical spacing between them is the cube root of the volume each one gets. Run that here, and the answer is about 5.6 light-years, which matches what we see. Run it in the nuclear star cluster, and the typical separation between neighbouring stars falls to roughly 1,000 astronomical units. The answer comes out at 1,000 astronomical units. Neptune orbits the Sun at about 30. So in the central parsec of our galaxy, the average gap between one star and the next is roughly 25 times the width of our planetary system. Not 5 light-years, not 1 light-year, a distance you could measure in the same units you use for planets. There is another way to feel that number, and it involves looking at the outer edge of our own solar system. The Sun does not stop at Neptune. It does not stop at the Kuiper belt either. Surrounding everything, at distances of tens of thousands of astronomical units, is the Oort cloud, a roughly spherical halo of icy bodies that we infer from the orbits of long-period comets, and whose outer boundary is usually placed somewhere around 100,000 astronomical units, about a light and a half years out. That is where the Sun's gravitational authority finally gives way to the galaxies. It is the true edge of our system, and it is 100 times further out than the typical distance between stars at the galactic centre. Turn that around, and the picture becomes uncomfortable. If you took our solar system, with its full cometary halo intact, and set it down in the nuclear star cluster, that halo would enclose not just our Sun, but something like 1 million other stars. It would not survive. It could not survive. The gravitational tugging from that many close neighbours would strip the outer material away in a fraction of the time our system has existed. Whatever a planetary system looks like in that environment, it is not shaped like ours. It is also worth being honest about how these density figures are arrived at, because the confidence in them is not uniform. Nobody has counted the stars in the central parsec one at a time. What astronomers do is measure the infrared surface brightness of the region, count the individual stars they can resolve, and then fit a model of the three-dimensional density profile that reproduces both. The result depends on the model, on assumptions about how many faint stars sit below the detection limit, on the mass function, on how the dust in the foreground is corrected for. The order of magnitude, 10 to the 7th per cubic parsec near 1/10 of a parsec, is robust, and has survived every serious attempt to knock it down. The precise number is not, and any script that quotes it to 3 significant figures is being more confident than the data, which means the sky there is not our sky. It is not our sky brightened, or our sky with more stars in it. It is a different kind of thing entirely. Work out the brightness. A star like our Sun, placed at a distance of 1,000 astronomical units, would appear at an apparent magnitude of about -11.7. For comparison, the full moon sits at about -12.7. So the nearest star would be within roughly 1 magnitude of the full moon, not spread across half a degree of sky the way the moon is, but concentrated into a single hard point. And behind that one, at 2,000 and 3,000 and 5,000 astronomical units, would be more and more and more. The arithmetic gives hundreds of thousands of stars brighter than anything that has ever appeared in Earth's night sky, distributed across the whole sphere in every direction. Let me put you there for a moment. You're standing on the surface of some rocky world, a few tenths of a parsec from the centre of the galaxy. It is what we would call night. Your world has turned its face away from whatever it orbits, and there is no darkness anywhere. The sky is a field of hard white points, thousands upon thousands of them bright enough to hurt if you look directly at anyone. The brightest hangs low and steady and casts a light comparable to a full moon, except that it is not a disk, it is a pinprick, and its light is white rather than grey. Your shadow is not a shadow. Look down, and you find a soft, overlapping confusion of shadows going out in every direction at once, each one faint, none of them dominant because there is no single source. The ground is lit well enough to read by. It will be lit well enough to read by tomorrow, and every day and every night after that, for as long as the world lasts. There is nothing overhead to sleep under. There is no direction you can face that is dark. The concept your species built its entire biology around, the daily withdrawal of the light, the reliable dark, the sky you turn your back on to rest, simply is not on offer here. The sky never goes dark. That is the first real loss on this journey, and I want to name it clearly because it is not a physics result. Nothing has changed about the laws. Gravity is behaving exactly as Newton described. Light is doing what light does. Not one equation is different from the equations in the room you're sitting in. What has changed is the furniture, how much of it there is, and how close together. And yet it is a genuine loss. Every human being who has ever lived has shared the experience of the sky going dark. Every one. It is one of a very short list of things that is true of all of us, across every culture and every century, and it turns out to be a local accident. It is a property of living in a thin, quiet, unpopulated suburb of a galaxy. Move to the good neighbourhood, and the first thing you lose is the night. There is a detail in the density measurements worth pausing on, because it was contested for a long time, and it matters more than it sounds. The way stellar density rises as you approach the centre can be described by a power law, and the question was what the index of that power law is right at the heart. Beyond about 1 parsec, the density rises with an index of roughly 1.8. Inside the central parsec, the profile flattens, and the index falls to something nearer 1.2. That flattening is still a rise. The density keeps climbing all the way in, but it climbs more gently than the outer trend would suggest. For about 2 decades, there was a real argument about whether the innermost region had a cusp of this kind or a core, meaning a flat central plateau. The distinction sounds technical, and it is not. A cusp and a core imply completely different dynamical histories for the whole cluster, different rates of stellar interaction, different answers to how the thing was assembled. Deep imaging has now come down on the side of a cusp, and it has also established that the nuclear star cluster is old and metal-rich, and that it did not form in a single event. It is a composite object, built over the galaxy's lifetime, part of it formed where it sits, and part of it delivered by smaller clusters that fell inward and were absorbed. One more thing about this cluster, because it is genuinely remarkable and rarely mentioned. Nuclear star clusters are common. Many galaxies have them, but every other one in the universe is, from our vantage point, a smudge of light, a bright unresolved blob at the centre of a distant galaxy, from which you can extract an integrated spectrum and very little else. The Milky Way's is the only nuclear star cluster close enough that current instruments can pick out tens of thousands of individual member stars, measure their positions and track their velocities one at a time. Everywhere else in the universe it is a statistic. Here it is a catalogue with entries in it. That fact is going to matter enormously in a few minutes, because the entire case for what sits at the centre of our galaxy was built star by star out of that catalogue. But before we get there, we should be honest about what a sky that crowded actually means for anything trying to live under it. Because 1,000 astronomical units between stars is beautiful from a distance, and it is something else entirely up close. It is not stable. In our part of the galaxy, stars essentially never meet. The numbers make it almost impossible. With 5.5 light years between neighbours and everything moving at a few tens of kilometres per second, a close encounter between 2 stars is a once-in-many billions of years proposition. Our Sun has been going around the galaxy for 4.5 billion years, roughly 20 complete orbits, and in all that time nothing has come close enough to seriously disturb the planets. The closest known approach in recent history was a small red dwarf called Schultz's star, which passed through the outer Oort cloud something like 70,000 years ago, and even that probably did little more than nudge a few comets. Encounters, for us, are a statistical curiosity. You can calculate the rate and then forget about it. Reduce the spacing to 1,000 astronomical units, and that changes completely. At the centre of the galaxy, stellar encounters stop being a footnote and become a governing process. The stars in the nuclear cluster are not only close together, they are also moving fast, orbital speeds of hundreds of kilometres per second, in a swarm rather than an orderly disk. 2 stars separated by 1,000 astronomical units and moving on independent paths will pass each other and pass close and do it again, and keep doing it for as long as they both exist. The whole cluster is a place where gravitational interactions between individual stars actually matter for what happens next. There is a structural difference here that is easy to miss and worth naming. Out where we live, the stars of the galactic disk all travel the same way. Broadly circular orbits, broadly in one plane, broadly in the same direction. It is traffic on a motorway. Everyone is going the same way at roughly the same speed, so relative velocities between neighbours are small, even though absolute speeds are large. The nuclear star cluster is not like that. Its stars orbit in every orientation, on paths tilted at every angle, going around in both directions. It is not traffic. It is a swarm. And in a swarm, two stars that pass each other are not drifting past at walking pace. They are closing at the full sum of their speeds. The consequences for anything smaller than a star are severe. A planetary system is a delicate arrangement held together by the fact that nothing large comes near it. Take that guarantee away, and the arrangement does not last. Outer planets get pulled onto wider and wider orbits until a passing star takes them entirely. Inner systems get stirred, their orbits made more elliptical, their careful long-term stability broken. Over the timescales that matter for anything to develop on a planetary surface, hundreds of millions of years, billions, a system in that environment is being repeatedly reshuffled by neighbours it never asked for. And it goes further than reshuffling. In a dense enough cluster, stars themselves can physically collide. That sounds like the kind of thing that should never happen, and for ordinary stars it very nearly never does. A star like the Sun is a small target. But not all stars are small targets. When a star like ours exhausts the hydrogen in its core, it swells enormously into a red giant, and its outer envelope becomes a thin, distended, weakly bound shell of gas hundreds of times the width of the original star. That is a very large cross-section. Two red giants passing near each other in a crowded cluster do not need to score a direct hit on their cores. They only need to graze envelopes, and the envelopes will do the rest, dragging, heating, stripping material away. This is not a speculative mechanism invented to fill a gap. It was proposed because there is a gap. Observations of the innermost region of the galaxy find a deficit of bright red giants. Fewer of them than the population models say there ought to be, especially in the innermost tenth of a parsec or so. Collisional stripping of their envelopes is the leading explanation. A red giant that loses its outer shell does not vanish, but it stops being bright in the way red giants are bright, and it drops out of the count. The details of exactly how efficient this process is, and whether it fully accounts for the observed deficit, are still being worked out. But the basic picture, that the environment is dense enough to physically damage stars, is not seriously disputed. Then there is the problem that has been sitting in the middle of this field since the 1990s, and which nobody has entirely closed. It is called the paradox of youth. Here is the shape of it. Within the central parsec, and even within the central tenth of a parsec, astronomers find young, massive, extremely luminous stars. Not a few, dozens. They are hot and blue and short-lived, which means they cannot be old. Their presence says star formation happened there, and happened recently in astronomical terms. The trouble is that star formation should be effectively impossible in that location. Stars form when a cold molecular cloud collapses under its own gravity, and that collapse is a delicate business. The cloud has to hold itself together against everything trying to pull it apart. Close to a 4 million solar mass black hole, the tidal field is strong enough that a typical molecular cloud is pulled apart faster than it can fall together. The gas gets sheared out before it can ever reach the density where a star ignites. By the standard account, that region should be sterile. There are two families of answer, and both are uncomfortable. The first says the stars formed somewhere safer, further out, and then migrated in. The problem is that moving a star from a comfortable radius into the central parsec, intact, on the timescale available before it dies, is dynamically very difficult. You need a mechanism that delivers whole star clusters inward efficiently, and the candidates all struggle. The second says the stars formed right where they are, but not out of an ordinary cloud, out of a dense self-gravitating disk of gas that had already settled into orbit around the black hole. A structure like that could be compressed enough to fragment locally even in a strong tidal field. This idea has real support from the observations, because the young stars in the central region do not appear randomly distributed. They appear to lie in one and possibly two coherent orbital planes. That is exactly what you would expect if they condensed out of a disk, and it is very hard to explain if they arrived independently from elsewhere. That is the leading answer today. It is not a closed case, and it has been open for roughly 3 decades. Among those young massive stars is a group catalogued as IRS-16, and they are worth mentioning because of what they do rather than what they are. Stars that massive drive enormously powerful stellar winds. They are shedding their own material into space continuously, at high speed. Those winds are the main source of the gas that surrounds Sagittarius A star, which means that in principle, the black hole at the centre of our galaxy has a supply. Gas is being delivered to it constantly by its neighbours, and it eats almost none of it. We will come back to that. There is also a genuinely contested idea attached to all of this that deserves a mention with a warning label. It is called the galactic habitable zone argument, and it holds that the inner regions of a galaxy are hostile to long-lived biospheres for exactly the reasons we have been listing. Supernova rates high enough to sterilize, stellar encounters frequent enough to destabilize planetary systems, and background radiation elevated. The argument has been made carefully, and it has also been criticized carefully, and I would not present it as settled. But the density figures we have just been through are where whatever force it has comes from. And then there is the case that made everyone reconsider what they thought they knew, which is a small, faint object called G2. G2 was spotted heading towards Sagittarius A star, on a path that would take it very close indeed, with closest approach due in 2014. It looked like a cloud of gas and dust. Everybody expected the same thing. As it swung past the black hole, tidal forces would shred it, the debris would spread out, some of it would fall in, and there would be a bright accretion event, a flare, a genuine feeding. There were papers written in advance about what to look for. Telescopes were scheduled, it passed, and it largely held together. There was no dramatic flare. G2 came through its closest approach in something close to one piece and carried on. The most economical explanation, and the one now generally accepted, is that G2 was never a pure gas cloud at all. It was a star, an ordinary object with an ordinary gravitational grip on itself, wrapped in a dusty envelope that made it look like a cloud from a distance. The star held. The dust made the picture. I want to draw a line under this part before we move on, because it matters for what comes next. Everything in this part, the encounters, the stripped giants, the impossible young stars, the cloud that turned out to be a star, is ordinary gravity. Newton would have recognized every bit of it. Nothing here requires relativity. Nothing here is a distortion of reality in any meaningful sense. It is simply what happens when you take the same physics you have always had and run it in a room that is 50 million times more crowded. The rules have not changed yet. Only the density has. To find the first place where the rules themselves stop working, you have to stop looking at the crowd. You have to pick one star out of the hundreds of thousands and watch it, and keep watching it for longer than most careers last. On the 16th of February, 1974, 2 radio astronomers named Bruce Ballack and Robert Brown pointed an interferometer in Greenbank, West Virginia, at the middle of the galaxy and found something small. That is the beginning of this story, and it is worth appreciating how modest a beginning it is. They were not hunting for a black hole. The idea that a supermassive black hole might sit at the centre of the Milky Way had been floated, but it was one possibility among several, and there was no particular reason to believe it. What Ballack and Brown were doing was mapping the radio emission from the galactic centre at high resolution, and what they found in the middle of a broader, messier region of radio brightness was a source that was compact. Very compact. Far too small and far too precisely placed at the dynamical centre to be an ordinary object. They published it. And then, for 8 years, the thing did not have a name. In 1982, Robert Brown fixed that. He called it Sagittarius A star, and he chose the asterisk deliberately. In atomic physics, an asterisk after a symbol denotes an excited state, an atom holding more energy than its ground configuration. Brown thought the source was, in his word, exciting. So he borrowed the notation. It is one of the very few object names in professional astronomy that is a pun, and it made it through peer review and into permanent use, and every paper written about the centre of our galaxy for the last 40-odd years has carried a small joke in its title. But a name is not a measurement. Finding a compact radio source tells you almost nothing about what it is. It could be a very dense star cluster. It could be some exotic configuration of matter. It could be a black hole. To distinguish between those, you need to know the mass, and you need to know how tightly that mass is packed, and there is no way to read either off a radio image. So how do you weigh something you cannot see? you watch something orbit it. This is the oldest trick in gravitational astronomy, and it has never stopped being the best one. If an object is going around another object, the shape and period of that orbit tell you the mass of what it is going around, and they tell you without requiring any assumption whatsoever about what that mass is made of. It could be gas, dust, stars, dark matter, or something nobody has thought of. Kepler's laws do not care. Give me the size of the ellipse and the time it takes to complete, and I will give you the enclosed mass. The centre of our galaxy, it turns out, has a whole population of stars doing exactly that. Astronomers call them the S-stars, and they are the finest instruments in observational relativity anywhere outside our own solar system. Not because they are exotic, but because they are simple. Each one is a clean test particle on a clean orbit around a single dominant mass, which is a situation physicists dream about and almost never get. The most important of them is called S2. S2 goes around Sagittarius A star once every 16.05 years. Its orbit is not a gentle circle. It has an eccentricity of about 0.88, which makes it a long, thin ellipse. At its most distant, it is nearly 2,000 astronomical units from the centre, drifting slowly. At its closest, it comes within 120 astronomical units, inside the distance from our Sun to the outer Kuiper belt. And it does that at a speed we will get to shortly, because it is the number this part is building toward. There is a detail about S2 that connects straight back to the last part, and it is a nice piece of unfinished business. S2 is not an old star quietly ending its days. It is young, hot, and blue. A B-type star weighing something like 14 times the mass of our Sun, of the kind that lives for a few tens of millions of years and then dies. Which means S2 is itself an instance of the paradox of youth. It is far too young to have drifted in from the outer galaxy, and it is sitting in the one place where forming a star should be impossible. The single most important object in the study of the galactic centre is also one of the objects that should not be there. Nobody has resolved that, and everybody uses the star anyway. S2 is also not alone. Astronomers have now catalogued dozens of stars on tight orbits in that region, and mapping several of them at once turns out to be more powerful than mapping any one. If a large amount of extra mass was spread through the volume inside S2's orbit, a swarm of stellar remnants, say, or a concentrated overdensity of dark matter, it would perturb the different orbits in different predictable ways. Comparing them lets you place limits on how much unseen extended mass can be hiding in there. The limits are tight. Whatever is at the centre is very close to a single point. 16 years is not a long time in astronomy. It is a very long time in a human career. That is the fact that sits underneath everything else in this part, and I do not want to skate past it. To establish that S2 was on a closed orbit at all, you had to watch it long enough to see it curve. To measure the orbit properly, you had to watch it complete one. To check that the orbit was doing what general relativity predicted rather than what Newton predicted, you had to watch it come back around and do it again. There is no way to speed this up. There is no simulation you can run instead. You point a telescope at one faint star buried in a crowded field, behind 30 magnitudes of dust, and you take its position, and then you wait a year, and you do it again. 2 groups did this, independently, in parallel, for 3 decades. One was led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics in Germany, working with telescopes in Chile. The other was led by Andrea Ghez at the University of California, Los Angeles, working with the Keck telescopes in Hawaii. They used different instruments, different techniques, different data reduction, and different naming conventions. The star the European group calls S2 is the star the American group calls S0-2. For 30 years, 2 teams on opposite sides of the world measured the same handful of stars and checked each other without meaning to. A very large part of why the result is trusted is that neither of them could have quietly fooled themselves without the other noticing. The instruments had to be invented as they went. In the early 1990s, imaging faint stars in the galactic centre at the resolution required simply was not possible from the ground, because the atmosphere blurs everything. The technique that solved it is called adaptive optics, measuring the atmospheric distortion many times a second and physically deforming a mirror to cancel it out in real time. It went from a specialist novelty to standard equipment across this campaign. Then came dedicated infrared instruments on the Very Large Telescope in Chile called NACO and Symphony. And then, in 2016, the thing that changed everything, gravity, an instrument that combines the light from all 4 of the 8-meter telescopes at Paranal into a single interferometric signal. giving an angular resolution no individual telescope could reach. Let me put you at Paranal in May of 2018, because this is the night the campaign had been building toward. It is a mountain in the Atacama, more than 2.5 kilometres up, in one of the driest places on the surface of the Earth. 4 enormous telescopes are open to the sky, and they are not observing independently. Their light is being carried underground through tunnels, along paths whose lengths are controlled to within a fraction of the wavelength of the light itself, to be combined in a laboratory beneath the summit. The target is one star. Not a galaxy, not a nebula. One star, out of the hundreds of thousands packed into that region, currently sweeping through the closest point of its 16-year orbit. Nobody in the building can see it. Nobody ever has. It is invisible in every optical instrument ever constructed, and everything about this measurement is inferential. A position derived from interference fringes, a velocity derived from the stretching of spectral lines. Some of the people watching the data come in have been waiting 16 years for this pass. A few of them have been waiting for 2 of them, and the quantity they are hunting for is a shift in the star's light of well under 1%. That is what the measurement of the centre of our galaxy actually looks like. Not a moment of discovery, a scheduled appointment that took a generation to arrive. I find the patience here genuinely moving, and I think it is worth saying so plainly. There are branches of science where you can have an idea in the morning and test it in the afternoon. This is not one of them. The people who did this work committed a substantial fraction of their working lives to watching one star go around 1.5 times. They did it knowing that if they were wrong about something fundamental, they would not find out quickly, and that whatever they published would sit in the literature being checked by the other team for as long as it took. Nearly 2.5 complete orbits of S2 have now been tracked. That is the entire dataset. That is 30 years of 2 research groups' attention, and it comes to 2.5 laps. What it bought is worth every year. From the orbit you get the enclosed mass, 4,297,000 solar masses, now known to about 1%, together with the distance to 8,277 parsecs. From the pericentre you get something even more important, a limit on how small that mass has to be. S2 comes within 120 astronomical units of the centre, and does not hit anything, is not disrupted, and continues on a clean elliptical path. That means all 4.3 million solar masses are packed inside a region smaller than the planetary part of our solar system. There is no known way to do that with ordinary matter. A cluster of stars that dense would collapse or evaporate on a timescale far shorter than the age of the galaxy. A cluster of stellar remnants, neutron stars, dead white dwarfs, runs into the same problem. Every configuration anyone has proposed either falls apart or falls in. By the time you have S2's orbit in hand, the black hole interpretation is not one possibility among several. It is the only one left standing that does not require inventing new physics. In 2020, the Nobel Prize in Physics went to Reinhard Genzel and Andrea Ghez for that work. They shared it with Roger Penrose, whose 1965 theorem had shown mathematically that singularity formation is a generic consequence of general relativity rather than an artifact of overly tidy assumptions. The theoretical result that made it reasonable to expect these objects to exist in the first place. Ghez was the 4th woman ever to receive the Physics Nobel. So, everything this video is going to claim about the last few million kilometres, every clock ratio, every boundary, every failure of an ordinary concept, rests on this, not on a theory, on one star, 2 teams, and 30 years of not looking away. And in May of 2018, at the closest point of its orbit, that star did something Newton could not account for. At its closest approach, S2 comes within 120 astronomical units of Sagittarius A star. Expressed in the units that matter here, that is about 1400 Schwarzschild radii. Still a long way out, in the sense that the star is nowhere near the horizon and is in no danger from it. But it is close enough for the field to be strong, and the star responds to that field in a way you can see from 27,000 light-years away, if your instrument is good enough. At pericentre, S2 is travelling at 7,650 kilometres per second. Let that number settle. 7,650 kilometres in 1 second. The Earth goes around the Sun at about 30 kilometres per second. The fastest spacecraft humans have ever built, the Parker Solar Probe at the bottom of its plunge toward the Sun, reached about 192 kilometres per second, and that was a record that stood as one of the great engineering achievements of the century. S2 is doing 40 times that. It is moving at 2.5% of the speed of light, and it is not a probe, it is a star. 14 times the mass of our Sun, several times its width, an entire luminous object weighing something like 28,000 trillion kilograms, and it is moving at 2.5% of light speed. There is nothing else like this available to observe. In our solar system, the fastest thing in a natural orbit is Mercury, at about 47 kilometres per second, and Mercury's relativistic effects are famously subtle. Here the effects are not subtle at all. What gravity was looking for in May of 2018 was a shift in the wavelength of S2's light, and there are two distinct relativistic contributions to it. The first is the transverse Doppler effect. In special relativity, a moving clock runs slow as measured by someone at rest, and a star's emitted light is a kind of clock. It oscillates at a characteristic frequency set by the atoms producing it. If the source is moving fast, that frequency arrives lower than it left, and this happens regardless of whether the star is coming toward you or going away. It is a pure consequence of speed. Newtonian physics has no such effect at all. The second is gravitational redshift. Light climbing out of a gravitational well loses energy on the way up, and losing energy for light means getting redder. S2 at Pericenter is sitting deep in the well of a 4 million solar mass object, and every photon it emits has to climb out of that well to reach us. Again, this effect does not exist in Newtonian gravity, not a small version of it. It is simply not in the theory. Both effects push the same way, and both are small. Combined, they amount to a fraction of 1% of the light's wavelength, riding on top of the ordinary Doppler shift from the star's motion along our line of sight, which is much larger. Separating the relativistic part from the classical part requires knowing the orbit precisely, which is what those 30 years brought. The result was published in 2018, and the way it was reported deserves a moment, because it is a model of how to state a physics result honestly. Rather than announcing that Einstein was right, the collaboration defined a parameter. They called it F. If F equals 0, the data match the Newtonian prediction, no relativistic shift at all. If F equals 1, the data match general relativity exactly. Any value in between corresponds to a partial effect, which no theory actually predicts, but which is a perfectly sensible way to quantify how far the measurement sits from each end. They measured F equal to 0.90 plus or minus 0.09. That is 1 standard deviation from general relativity's value of 1 and 10 standard deviations from Newton's value of 0. A refined analysis the following year, with more data and better handling of the systematics, gave F equal to 1.04 plus or minus 0.05. The relativistic shift is there, at the predicted size in the light of a star orbiting the centre of our galaxy. 2 years after that came the second detection, and in some ways it is the more beautiful one. An orbit under Newtonian gravity, around a single point mass, is a closed ellipse. The planet or star goes around and comes back to exactly where it started, and traces the same path forever. Under general relativity, it does not. The ellipse itself slowly rotates. The point of closest approach advances a little further round with each circuit, so the orbit traces out a slowly turning rosette rather than a fixed oval. This is called Schwarzschild precession. You have heard of this effect before, even if the name is unfamiliar, because it is the one that made Einstein's reputation. Mercury's orbit had been known since 1859 to precess by a small amount that Newtonian gravity could not account for, 43 arc-seconds per century, after every other influence had been subtracted. Astronomers spent decades looking for an unseen planet to explain it. In 1915, Einstein calculated the effect from his new field equations and got 43 arc-seconds per century, and he later said the discovery gave him palpitations. That was 43 arc-seconds per century for Mercury. For us too, the same effect amounts to roughly 12 arc-minutes per orbit, around 1,000 times larger per revolution in the prograde direction, meaning the orbit turns the same way the star goes around. The gravity collaboration reported the detection in 2020, and it matched the prediction within the uncertainties. So there are now two independent relativistic effects measured in the same star's motion using different physics extracted from different features of the data. That is a very hard thing to fake. Now let me convert all of that into the currency this video actually deals in, which is time. Combine the two contributions, the gravitational one from sitting in the well and the velocity one from moving at 2.5% of light speed. And at pericenter S2's clock is running slow relative to ours by about 3 parts in 10,000. That is 3 parts in 10,000. Over the course of 1 year, that is roughly 2.75 hours. Over one full 16-year orbit, S2 accumulates a lag of something like 2 days. It comes to 2 days, out of 16 years. If you had set a watch running on S2 when it last passed close by, and set an identical watch running on Earth, and brought them back together at the next pericenter in about 2034, they would differ by about 2 days. I want you to notice how small that is, and then I want you to notice what it means. It is small. 2 days in 16 years is a discrepancy you would never spot without an atomic clock. It is nothing you could feel, nothing that would affect anyone's life, nothing that a person living on a planet around S2 would ever have cause to think about, but it is not zero. And 2 parts ago, at 1 light year out, it was 1 part in a million, a fraction of a second per century. We have moved from a fraction of a second per century to 2 days per orbit, and we have done it by moving from 1 light year to 120 astronomical units. That is the flat curve lifting off. This is the first radius on the entire journey where the effect stops being an abstraction and becomes a reading on an instrument, not a prediction, not a calculation from theory about what would happen if you could get close enough, a measurement taken from a mountain in Chile of a real object that is really out of step with us. Newton's description of gravity has done everything asked of it for the whole trip so far. It survived the crowded sky. It survived the stellar encounters. It survived the whole nuclear cluster. Here, at 120 astronomical units, it finally produces the wrong answer and something else produces the right one. And S2 is not even the extreme case. Astronomers have found stars on tighter orbits still. One catalogued as S4716, reported in 2022, completes an orbit in only about 4 years and closes to roughly 100 astronomical units at something like 8,000 kilometres per second. Others, including objects called S62 and S4711, have been reported with short periods, and there have been claims of pericenter speeds several times higher than S2's. Those extreme claims are contested, and I would not lean on them, but the direction of travel is clear. Every time the instruments improve, someone finds a star that is closer and faster than the last one. It is worth saying what the raw material of these measurements actually is, because the phrase "they measured the redshift" hides a lot of craft. What arrives at the telescope is a spectrum, the star's light spread out by wavelength, with dark absorption lines cut into it at the specific wavelengths where atoms in the star's atmosphere have removed energy. Those wavelengths are known in the laboratory to extraordinary precision because they are set by atomic physics, and atomic physics does not vary. So you look at where the lines actually landed, compare that with where they should have been, and the difference is the shift. It is bookkeeping in a sense, a comparison between an observation and a number in a reference table. What makes it hard is that the star is faint, the field is crowded, the dust is thick, and the effect you're hunting for is a fraction of a percent buried under a much larger ordinary Doppler shift that you have to model away first. S2 has since become a permanent instrument rather than a one-time result. Work published through 2025 and 2026 continues to use its precession as a laboratory for testing extensions and alternatives to general relativity, placing bounds on hypothetical violations of Lorentz symmetry, checking whether the central mass behaves as a smooth point or shows signs of being granular, and narrowing the space where a second, smaller black hole could hide. One star, going around once every 16 years, has quietly become a standing test bench for fundamental physics. We have crossed the line where our physics changes. From here inward, general relativity is not a correction to be applied, it is the description, and 4 years after S2's pericenter, we finally got a picture. The apparent size of Sagittarius A star, as seen from Earth, is about 52 microarcseconds. A microarcsecond is a millionth of an arcsecond, and an arcsecond is a 3,600th of a degree. To get a feel for 52 microarcseconds, the standard comparison is a donut placed on the surface of the moon and viewed from your back garden. That is the target. That is what somebody decided to photograph. The angular resolution of a telescope depends on the wavelength you're observing at and the diameter of the aperture you're observing with. To resolve a donut on the moon at radio wavelengths, you need an aperture roughly the size of the Earth. Nobody can build a dish that size. But you do not have to because of a technique called very long baseline interferometry. If you observe the same source simultaneously from telescopes scattered across the planet and record the incoming waves with atomic clock timing precision, you can afterwards combine those recordings and extract the interference pattern that a single Earth-sized dish would have produced. You do not get the light-gathering power of a planet-sized mirror. You do get its resolution. That is the Event Horizon Telescope. It is not one instrument. It is an agreement between observatories on several continents to point at the same thing at the same moment and ship the hard drives somewhere central. The observations were taken in April of 2017. The image of Sagittarius A star was released on the 12th of May, 2022. That gap is 5 years, and the delay is one of the most interesting parts of the story because it points at something physical. The same campaign that observed Sagittarius A star also observed M87, the supermassive black hole at the center of a giant elliptical galaxy about 55 million light-years away. And that image came out in 2019, 3 years earlier. M87 is a far more distant and far more difficult-sounding target, and it was processed first. Why? Because Sagittarius A star will not sit still. The characteristic timescale on which gas near a black hole's horizon orbits scales with the mass. M87's black hole weighs something like 6.5 billion solar masses, so its innermost gas takes days to complete a circuit. During an observing run, the source is effectively frozen. Sagittarius A star weighs 4.3 million, which is about 1,500 times less, and its innermost gas orbits in minutes. Over the course of a night's observing, the thing being photographed rearranges itself completely, several times. The collaboration's own description was that it was like trying to photograph a puppy that will not sit still. Every conventional imaging algorithm assumes the source is static while you collect the data. Here that assumption fails badly, and reconstructing a meaningful image required developing methods that could handle a source varying faster than the observation. What was eventually released is not a snapshot. It is a statistical average over a fundamentally variable object, and the collaboration was careful to say so. What the image shows is a bright ring with a dark center. The ring diameter measured 51.8 microarc seconds, with a stated uncertainty of plus or minus 2.3 at 68% credibility. And that phrasing matters because it is a Bayesian credible interval derived from image reconstruction rather than a conventional error bar. It means something slightly different, and the difference is worth not glossing over. Now, the dark region in the middle is not the event horizon. This is the single most common misunderstanding about these images, and it is worth clearing up carefully, because it also sets up everything in the next few parts. The horizon of Sagittarius A star has a radius of 12.7 million kilometres, but light passing near a black hole does not travel in straight lines. The geometry bends it. Photons that would have missed the horizon get curved into it. The result is that the silhouette cast against the surrounding glow is bigger than the horizon itself, by a specific and calculable factor. For a black hole of this kind, the shadow diameter comes out at about 2.6 Schwarzschild radii, rather than 2, roughly 33 million kilometres instead of 25. So the dark patch in that image is not a hole punched in space at the size of the horizon. It is a shadow, and it is a shadow that is larger than the object casting it, because the light itself is being bent around the object on its way past. That is not a metaphor. It is the actual geometry, and the fact that the measured ratio came out at the predicted value is one of the cleanest confirmations of general relativity in the strong field regime that anyone has ever obtained. There is a coincidence buried in all of this that made the whole enterprise possible, and it deserves mentioning. M87's black hole is about 1,500 times more massive than ours, which makes it about 1,500 times larger. It is also about 2,000 times further away. Those two factors very nearly cancel, which is why the two shadows subtend comparable angles on our sky, and why a single instrument built to a single specification could image both. If either number had been different by a factor of 10, one of those two images would not exist. Let me stop here for a moment and put together what we have. We started at the beginning, 26,900 light-years out. We established that the object at the center has a measured mass and a measured distance, and that its horizon would fit inside the orbit of Mercury. We travelled inward and found that for almost the entire journey, nothing relativistic happens at all. 1 light-year out, the clocks still agree to a part in a million. we found that what does change first is the sky, which fills with stars until night stops existing, and that the density which produces that sky also makes the whole region dynamically unstable. We watched one star for 30 years and from its orbit alone, weighed the thing at the centre and bounded its size. We caught that star's light redshifted and its orbit precessing at 120 astronomical units in exactly the amounts general relativity predicts, and in amounts Newton cannot produce at all. And now we have a silhouette, measured to be 2.6 Schwarzschild radii across, which is precisely what the same theory says it should be. That is a complete case, built from 4 independent directions, and every one of them agrees. It is also, without exception, the view from outside. Everything up to this point has been something we can look at. From here inward, that stops. There is no image of the innermost region, and there will not be one, because there is nothing there to image in the ordinary sense. What we have instead is the mathematics. The same mathematics that has now been checked against a redshift, a precession and a shadow, and has passed each time, and what the mathematics does from here is start taking things away. Before we go, one more thing about this object that has always struck me as strange. Sagittarius A star flares. Roughly daily, in the infrared and in X-rays, it brightens by factors of tens over minutes to hours, then subsides. In 2018, the gravity instrument managed to track the apparent position of the source during several of these flares and found the bright centroids moving, circling the black hole at radii of roughly 6 to 10 Schwarzschild radii at orbital speeds near 30% of the speed of light. We have watched matter go around Sagittarius a star at nearly a third of light speed, not inferred it, watched it. There is also, notably, no jet. M87 produces one of the most spectacular relativistic jets in the observable universe, thousands of light-years long. Ours produces nothing of the sort, and whether that is an orientation effect, a consequence of the low accretion rate, or something genuinely different about the object, nobody has settled. And the quietness we see is almost certainly temporary. There is good evidence that Sagittarius A star has been very much louder in the past, and not in the distant past either. The clearest piece of it was found in 2010, when astronomers analysing gamma-ray data noticed 2 enormous lobes of emission extending above and below the plane of the galaxy, symmetric, centred on the galactic centre and reaching roughly 25,000 light-years in each direction. They are called the Fermi bubbles, after the telescope that found them, and they are larger than any structure anyone expected the Milky Way to contain. 10 years later, an X-ray survey found even larger counterparts wrapped around them. Structures like that do not form quietly. The most economical explanation is that the galactic centre had a major outburst, and that what we are looking at is the fossil of it. How recently? Independent work on the ionization of the Magellanic Stream, a long ribbon of gas trailing behind our satellite galaxies, points to a burst of intense radiation from the galactic centre roughly 3.5 million years ago. Our ancestors were already walking upright in East Africa when it happened. And there is a shorter-term hint as well. X-ray light reflecting off molecular clouds near the centre suggests that Sagittarius A star was orders of magnitude brighter a few hundred years ago than it is now. Some of what we detect bouncing off those clouds left the black hole around the time of the European Renaissance. So the object we photographed in 2022 is not a black hole that has always been asleep. It is one that is currently between meals. Now we go inward, past the last thing anyone has photographed, and the first thing to disappear is the orbit itself. An orbit is such an ordinary thing that it takes an effort to see it as an achievement. Everything in the sky is doing it. The moon goes around the Earth goes around the sun goes around the galaxy, and none of it requires maintenance. Nobody is steering. There is no fuel being burned. A stable orbit is the natural resting state of anything moving in a gravitational field that has not been disturbed, and it will persist essentially forever if nothing interferes. That permanence is why we can talk about the Earth's year as a fixed quantity, why eclipses can be predicted centuries ahead, and why the solar system has the same architecture today that it had before there were animals to look at it. That permanence has a limit, and the limit has a radius. Around a non-rotating black hole, the innermost stable circular orbit sits at 3 Schwarzschild radii. For Sagittarius A star that is about 38 million kilometres from the centre, hold that against the comparison we set up at the very start. Mercury orbits the Sun at 58 million kilometres, So the last stable orbit around the black hole at the centre of our galaxy sits comfortably inside Mercury's distance from our star. Everything else in this video from here on takes place inside a region you could fit into the inner solar system with room to spare. What innermost stable means is worth spelling out, because the phrase does not carry its own weight. Out here, orbits are forgiving. Nudge the Earth slightly, give it a small push inward or outward, and it does not spiral into the sun or fly off into space. It settles into a slightly different ellipse and carries on. The orbit is stable in the technical sense. Small perturbations produce small changes, and the system returns to something like its previous behaviour. This is true for every orbit in the solar system, and for the overwhelming majority of orbits anywhere in the universe. Inside 3 Schwarzschild radii, that stops being true. There, a circular orbit still exists as a mathematical solution, but it is unstable. Nudge it inward by any amount at all, however tiny, and it does not settle into a slightly tighter circle. It spirals in. Nudge it outward and it leaves. There is no restoring behaviour, no settling, no equilibrium. The orbit sits on a knife edge, and the universe is full of knives. In practical terms, this means that inside 38 million kilometres, nothing can simply be in orbit. Nothing can quietly go around and around indefinitely. Everything either falls or leaves. The category orbiting object has been retired. This is not an abstract statement. It is why accretion disks around black holes have an inner edge, and why that edge is where the emission peaks. Gas spiralling inward through a disk loses energy gradually and moves inward gradually, orbit by orbit, until it reaches this radius, and then it stops being gradual. It falls. That transition, from slow inward drift to plunge, is the single most important structural feature of any accreting black hole, and it happens exactly here. One caveat, which we'll pick up properly in a moment. 3 Schwarzschild radii is the figure for a black hole that is not rotating. Rotation changes it, and it changes it a great deal. For an object spinning rapidly, the innermost stable orbit for material going around the same way as the spin moves inward, in the limit of maximum possible rotation, all the way down to half a Schwarzschild radius. Sagittarius, a star, does rotate, and probably rapidly, so its real innermost stable orbit is closer in than 38 million kilometres. We're using the non-rotating number because it is the clean one to think with, and because the qualitative story is identical. Now we come to the clocks. For an object in a circular orbit, the rate of its clock relative to a distant one is the square root of 1, minus 3/2 of the Schwarzschild radius divided by the orbital radius. Put in 3 Schwarzschild radii and the fraction inside becomes exactly 1/2. The square root of 1/2 is 1 over the square root of 2. The number is 0.707. That is 70.7%. At the last stable orbit around Sagittarius, a star, a clock runs at just over 7/10 the rate of a clock at home, which means 1 year spent there corresponds to 1.414 years back on Earth. There is a distinction hiding in that formula that is worth pulling out, because it tells you something about where the slowing comes from. If instead of orbiting you simply hovered at that radius, engines burning hard, holding position, not moving at all relative to the distant stars, the expression would be different. It would be the square root of 1 minus the Schwarzschild radius over the radius, without the 3/2, and at 3 Schwarzschild radii that comes out at about 82% rather than 71. So the hoverer's clock runs slow too, but noticeably less slow than the orbiter's. The difference between those two numbers is the contribution from motion. The orbiter is not only sitting deep in a gravitational well, which slows their clock, they are also travelling extremely fast, which slows it further. Two separate effects from two separate parts of relativity. One from the curvature of space and time around a mass, one from velocity alone, stacked on top of one another, and this is exactly the same pair of effects we met back at the satellites overhead, where altitude and speed pulled in opposite directions and left 38 microseconds a day. Here they pull the same way, and they leave 30%. There is also a piece of physics attached to this radius that explains why black holes are the brightest objects in the universe, despite emitting nothing themselves. As gas spirals inward through a disk, it has to shed energy to move to a tighter orbit, and that shed energy comes out as radiation. Add up everything radiated between infinity and the last stable orbit, and you find that for a non-rotating black hole, something like 5 or 6% of the infalling matter's rest mass energy has been given off as light before it ever reaches the plunge. For a rapidly rotating one, the figure can climb toward 40%. Set that against nuclear fusion, which is the process powering every star in existence, and which converts about 0.7% of the mass it processes into energy. Accretion onto a black hole is roughly 10 times more efficient than the fusion in the heart of the Sun, and for the fastest spinners it is more than 50 times. Nothing else in the universe converts mass into light this well. The most efficient engine we know of is a hole, and the fuel is whatever falls in. Let me put you in that orbit. You are 38 million kilometres from the centre of the galaxy, closer to it than Mercury is to the Sun, going around once every few minutes at a substantial fraction of the speed of light. Your watch reads 1 second per second. It always has and it always will. There is nothing wrong with it, nothing sluggish about it, nothing you could detect by any test. Your heart is beating at its normal rate. Your breath comes at its normal interval. Ahead and below, the accretion glow is a hard sheet of light, and set into it is a dark circle that is not a hole in the light but a shadow, and it is the last thing you will ever see the far side of. Behind you, out past all of it, is the rest of the galaxy, 100 billion stars and one of them yours. And that galaxy is running fast, not visibly, not in any way you could watch happen. But every second you spend here, 1.414 seconds pass out there. You settle in. You stay a decade because you want to see how the disk behaves, and when you leave, 14 years have gone by at home. Nobody did anything to you. You have simply been keeping time correctly in a place where correct time is a different quantity. That is not a paradox. Nothing has gone wrong. It is an accounting difference, and both sets of books are right. Compare it with what we had 2 parts ago. S2, at 120 astronomical units, runs about 2 days slow per 16-year orbit. Here, at 38 million kilometres, the discrepancy is roughly 4 months per year. We have gone from a lag you would need an atomic clock to notice, to a lag you could measure with a calendar, and the distance we cross to do it is about 120 astronomical units. Call it 18 billion kilometres, which sounds enormous and is a rounding error on a galactic journey. Line the whole ladder up, because the shape of it is the thing. At 26,900 light-years, the ratio is 1. At 1 light-year, the ratio departs from 1 by about a part in a million. At 120 astronomical units, it departs by 3 parts in 10,000. At 38 million kilometres, it departs by 30%. Almost all of the effect lives in the last stretch. We have been saying that since the second part of this video, and now you can see it happening. The curve was flat across a galaxy, and it is bending steeply inside the orbit of Mercury. There is something I want to name about this radius specifically, because it is the first genuine casualty of the trip. Everything lost so far has been circumstantial. The dark sky was lost because of where the stars happened to be. Planetary stability was lost because of crowding. Those are facts about furniture. This is different. At 38 million kilometres, 2 people who set their watches together and then part company can no longer keep those watches together, no matter what either of them does. There is no protocol they can agree on, no correction they can apply in advance, no technology that fixes it. One of them is simply going to be older. That is the first thing on this journey that is taken from you by the geometry itself rather than by the neighbourhood. And it is not the last. Because at this point you can still, at least in principle, hold a position. You can fire an engine and hover. You can decide to stay where you are relative to the distant stars and, with enough thrust, make it so. A little further in, even that stops being an option. Everything in the universe spins. Planets spin, stars spin, galaxies spin, and the reason is not mysterious. Angular momentum is conserved. Whatever rotation a cloud of gas has when it starts to collapse, it keeps. And as the cloud shrinks, that same amount of rotation is packed into a smaller and smaller object, so the spin rate climbs. It is the figure skater pulling in their arms, applied to objects the size of star systems. By the time a collapsing cloud has become a star, it is turning. By the time part of that star has become a black hole, it is turning fast. So Sagittarius A star rotates. The question is how fast, and the honest answer is that we're still working it out. Physicists describe black hole rotation with a dimensionless number, usually written as a lowercase a, running from 0 to 1. 0 means no rotation at all. 1 means the maximum a black hole can have. Spin it any faster, and the mathematics stops describing a black hole. Every real black hole sits somewhere between. For Sagittarius A star, estimates in the literature spread across a genuinely wide range. Analyses of the Event Horizon Telescope data, including work published in 2025 that used machine learning to pull additional structure out of the interferometric signals, favour a high value, something in the region of 0.8 to 0.9, with the spin axis inclined only slightly from our line of sight. Other approaches, using different assumptions about the accretion flow, land nearer 0.6. That is not a consensus with error bars. That is a real disagreement between methods, and I would rather tell you that than round it into a single confident figure. I also want to flag something odd that usually gets smoothed over. Several of these analyses find that the spin axis points nearly at us, face on. Out of all the orientations available in 3 dimensions, ours happens to be very close to the one that looks straight down the axis. That might be a coincidence. It might be a selection effect in the sense that a face-on system is easier to image cleanly, and so easier to get a confident answer out of. It might be telling us something about how the accretion flow is oriented. But it is worth noticing rather than accepting quietly, because unlikely alignments are usually a hint that something in the reasoning deserves a second look. Whatever the exact value, the rotation is doing something remarkable to the space around it, and this is where the next thing gets taken away. A rotating mass does not just curve space-time, it drags it. This is called frame dragging, and it is worth being precise about what is being dragged, because the everyday image is misleading. It is not that the black hole is stirring the gas around it like a spoon in coffee, although it does that too through ordinary friction and magnetic fields. Frame dragging is something else. The geometry itself, the reference frame against which motion is defined, is being carried around by the rotation. What counts as not moving at a given place is itself in motion. This effect exists around every rotating mass, including the Earth. It is fantastically weak here. A satellite mission called Gravity Probe B spent years measuring it around our planet and found the predicted effect, amounting to a drift of a few tens of milliseconds per year in a gyroscope's orientation. That is the entire influence of the Earth's rotation on the shape of local spacetime, and it took a purpose-built spacecraft with near-perfect gyroscopes to detect it at all. Near a rapidly rotating black hole, the same effect is not weak. Close enough in, the dragging becomes total. There is a region around a spinning black hole where the rotation of spacetime is so strong that nothing inside it can remain stationary with respect to the distant stars. Not because it is difficult, because it is not among the available options. You may have the most powerful engine that physics permits, pointed in the ideal direction, running at full output. It does not matter. Inside that region, every physically possible path involves going around. You're required to co-rotate. The region is called the ergosphere, from the Greek word for work, and the name is a promise we will come back to. Before we do, there is a consequence of all this rotation that reaches back into the last part and rearranges it. We said the last stable orbit sits at 3 Schwarzschild radii, and we said that figure holds for a black hole that is not spinning. Spin changes it, and it changes it in a way that depends on which direction you're going. If you orbit the same way the black hole rotates, the frame dragging is working with you, and the innermost stable orbit moves inward. For a maximally rotating hole, it moves all the way in to half a Schwarzschild radius, which is to say, right down onto the horizon itself. If you orbit against the rotation, the dragging is working against you, and the innermost stable orbit moves outward instead, to 4.5 Schwarzschild radii. So the answer to how close can something orbit is not one number. It is 3 numbers, depending on which way round you go, and the spread between them is a factor of 9. The geometry around a spinning black hole is not symmetric in the way we usually assume geometry is. Direction matters. Going clockwise and going anti-clockwise are physically different situations in a place where nothing is turning except space. I want to make sure this lands, because it is very easy to hear as a technicality and it is not one. Standing still is not something anyone thinks about. It is the default condition. You are doing it now. It is what happens when you stop doing things. Everywhere any human being has ever been, the option to remain where you are has been available, sometimes expensive, sometimes requiring effort against a current or a wind or a gravitational pull, but available in principle. Inside the ergosphere, that option has been removed from the list. Not made hard, removed. There is no amount of engineering, no amount of energy, no configuration of matter that permits it. Space is turning, and you are in it, and you turn. Note that this boundary is not the event horizon. The ergosphere lies outside the horizon, and it is not a point of no return. You can enter it, spend time inside it, and leave again. It touches the horizon at the poles and bulges out furthest at the equator, so it is not even a sphere despite the name. It is a flattened shell wrapped around the horizon like a squashed orange around its core. If the spin is as high as recent estimates suggest, that shell is substantial. There is a real volume of space around Sagittarius A star in which stay put is not a sentence that describes anything. And now we come to the promise in the name. In 1969, Roger Penrose, the same person whose singularity theorem would later share the 2020 Nobel with the people who weighed this black hole, pointed out something extraordinary about that region. If you drop an object into the ergosphere and arrange for it to split into two pieces there, with one piece falling into the black hole on a carefully chosen trajectory, the other piece can escape carrying more energy than the whole object had going in. The energy is not appearing from nothing, it is coming out of the black hole's rotation. The piece that falls in carries negative energy as measured from outside, and the hole spins down very slightly to pay for it. Do this repeatedly and you could in principle extract a substantial fraction of the rotational energy of a supermassive black hole. The size of that reservoir, for an object like Sagittarius A star spinning at 0.8 or above, is difficult to write down in a way that means anything. It is comparable to the total energy output of billions of stars over billions of years. It is sitting there, at the centre of our galaxy, in a form that is in principle extractable, and there is no mechanism anyone has ever proposed for actually getting at it that survives contact with reality. It is the largest useless battery in the Milky Way. There is one more thing to say about spin, and it points forward rather than back. There is a conjecture in general relativity called the no-hair theorem, and it says something almost absurd. A black hole, according to it, is completely described by exactly three numbers: its mass, its angular momentum, and its electric charge. That is the entire specification. Not what fell in, not what it was made of, not the history of anything. Three numbers, and any two black holes sharing those three numbers are identical in every respect, forever. If that is right, and every test so far is consistent with it, then Sagittarius A star, the most extreme object in our galaxy, is the simplest thing in it. Simpler than a hydrogen atom, which needs a wave function to describe properly. Simpler than a grain of dust. 4.3 million solar masses of whatever fell in over billions of years, reduced to three numbers. Testing that conjecture properly is one of the explicit goals of the next generation of the Event Horizon Telescope. Observing this object at higher frequencies and faster cadence could reveal whether its geometry really matches the rotating solution to Einstein's equations, or whether there is structure there that should not be. Finding a deviation would be one of the most important results in the history of physics. So far, nobody has found one. So, we have lost the stable orbit, we have lost the ability to stay where we are, both taken by the geometry, both at radii inside Mercury's distance from the Sun. What goes next is the ability to look away. Light travels in straight lines. That is one of the first things anyone learns about it, and it is one of the few pieces of physics that everybody remembers because you can check it. Shadows have sharp edges, beams are beams. A laser pointer does not curve. The correction that general relativity makes to that statement is small, and it is not a small correction. Light always takes the straightest available path, but straight is defined by the geometry it is travelling through, and near a mass that geometry is curved. So the light still goes straight, in the only sense the word can carry, and the path it traces is bent. We have known this since 1919, when Arthur Eddington's expedition photographed stars near the Sun during a total eclipse and found their apparent positions shifted by about 1 3/4 arc seconds, the amount Einstein had predicted, and twice the amount Newtonian reasoning could produce. That is the whole effect for the Sun. A shift you need a photographic plate and careful comparison work to see at all. Now take that effect and turn it up until light can travel in a circle. At 1.5 Schwarzschild radii from the centre of Sagittarius A star, about 19 million kilometres, the curvature reaches the point where a photon moving exactly sideways, perpendicular to the radial direction, is bent by precisely enough to keep it at the same distance. It does not fall in, it does not escape, it goes around. This radius is called the photon sphere, and it is a genuine surface in the sense that it is a specific distance from the centre, but it is a strange one, because nothing can stay on it. A photon on that circular path is balanced on an edge. Nudge it inward by any amount and it spirals into the black hole. Nudge it outward and it spirals away. Light orbits there, but no beam of light stays there long, because the universe is not smooth enough to leave anything undisturbed. What that means for an observer is one of the strangest experiences physics allows anyone to describe. You're holding position at the photon sphere. Doing that at all requires an enormous outward thrust. Enormous, but finite, which is worth noticing because it will not be true much further in. You're 19 million kilometres from the centre of the galaxy, and you turn your head so that you're looking sideways, along the tangent, straight out into what looks like empty space. You're looking at the back of your own head. It is not an illusion, and it is not a reflection. There is nothing there to reflect. The photons leaving the back of your skull, travelling perpendicular to the radius, follow the curved geometry all the way around the black hole and arrive back where they started, which is to say your eyes. The image is delayed by the light travel time around the circuit, so you are seeing yourself as you were a fraction of a second ago, and if you turn your head you will see the turn arrive after you have finished making it. Look the other way along the tangent, and you see the back of your head again, from the other side, having gone around the opposite way. There are two of you out there in the dark, both of them the same person, both of them slightly late. Look up, and the entire outside universe is not where it should be. Every star in the galaxy, every distant point of light, has been squeezed into a bright circle overhead, compressed by the bending of the light coming down to you. The circle does not fill the sky. It occupies a portion of it, and the rest, most of what you can see, is the black hole, an enormous darkness taking up the majority of your field of view. The universe has become something you look up into, through a hole, and the hole is getting smaller. Look down. There is nothing down there. Not darkness in the sense of an unlit surface. There is no surface. There is nothing for light to come from. I want to connect this back to the picture we talked about a couple of parts ago because the photon sphere is the explanation for a number we quoted and did not justify. The Event Horizon Telescope image shows a dark region with a diameter of about 2.6 Schwarzschild radii, and we said that this is larger than the horizon, which is 2. The reason is exactly this bending. The silhouette you see against the surrounding glow is not the outline of the horizon. It is the outline of the region from which no light can reach you, and because light paths curve inward near the hole, that region is bigger than the horizon. Photons that were aimed to pass at 1.5 Schwarzschild radii get captured. Photons aimed a little further out get bent but escape, and they are what make the bright ring. The size of the shadow is set by the photon sphere and by how much the geometry curves the paths on their way past. So when you look at that image, you are not looking at a black hole. You are looking at the shape of the paths light takes near one. There is more that happens to vision here, and it gets stranger the faster you are moving. If you are not hovering but falling, and eventually everything falls, then the aberration of light takes over. This is an ordinary special relativistic effect, the same one that makes rain appear to come at you from the front when you run through it. The faster you move, the more the incoming light appears to arrive from ahead. For an observer falling rapidly inward, the whole sky crowds forward into a shrinking cone in the direction of travel. Everything you can see gets pushed into a smaller and smaller patch, and that patch gets brighter, as the same amount of light is concentrated into less of your field of view. And the colours change. The light coming from behind you, from the universe you're leaving, is blue shifted by your motion and reddened by having to catch you, and which effect wins depends on where exactly you are and how fast you're going. The light from ahead is treated the opposite way. The outside universe does not just move in your sky, it changes colour as it moves. Now I want to say something carefully, and then move on without explaining it, because it belongs to the end of this video and not here. Through all of that, the head you can see the back of, the sky compressed into a circle, the colours shifting, the geometry doing things to light that no equipment on Earth could survive. One number has not changed. If you take out a ruler and a clock and measure the speed of the light in front of you, in your own hands, in your own laboratory, you get 299,792.458 kilometres per second. Exactly the value it has in every physics textbook on Earth. Exactly the value it had before you left. That is not an approximation. It is exact. It has not budged, and it will not budge, no matter how deep you go. Hold on to that. We will need it. For now, notice what has just been taken away. It is not sight. You can see perfectly well, your eyes work, photons are arriving and being detected. What has gone is the reliability of the relationship between what you see and where things are. Looking sideways shows you yourself. Looking up shows you a universe compressed and recolored and displaced from its true position. Vision has always been a straightforward matter of light coming from a thing in a straight line to your eye, and here the straight line is a circle. The eye is not failing. The geometry between you and everything else has stopped being the geometry your eye was built for, and there is one boundary left. It is the one everybody knows the name of, and everybody imagines wrongly, and it lies a little over 6 million kilometres closer in than where we are standing. It is also, of everything on this journey, the gentlest. Before we go there, one more consequence of light that can orbit, because it is the most beautiful thing in this part and it is currently at the frontier of what anyone can observe. A photon does not have to go around exactly once. It can go around twice, or 3 times, or any number of times, before spiralling out and escaping toward a distant telescope. Each of those paths carries an image. So the picture of a black hole is not a ring. It is an infinite nested sequence of rings, each one a complete image of the entire universe behind the hole, wrapped around and around, each successive one thinner and fainter than the last and sitting slightly closer to the shadow's edge. The bright ring the Event Horizon Telescope resolved is dominated by light that took a direct path. Inside it, packed into a band far too thin for current instruments to separate, is the first orbit image, and inside that the second, and inside that the third, converging on a boundary as the number of orbits climbs without limit. The spacing between successive rings shrinks by a fixed factor each time, a factor set purely by the geometry, roughly a factor of 500 in brightness per orbit for a non-rotating hole. And that factor depends only on the mass and the spin. Nothing else. Not the gas, not the magnetic field, not the accretion rate, none of the messy astrophysics that makes everything else about these objects hard to model. Which makes the photon ring the cleanest possible test of the geometry, if anyone can ever resolve it. Detecting the first subring and measuring its shape would be a direct measurement of the space-time around a black hole, with the astrophysics divided out, and it is one of the main scientific arguments for building the next generation of the array, potentially with elements in orbit to extend the baseline beyond the width of the Earth. So there is, in a precise and literal sense, an infinite number of pictures of the universe stacked around the edge of that shadow. Every one of them shows the whole sky. We have resolved the outermost, the rest are waiting, and the horizon itself sits about 6.3 million kilometres inside the photon sphere. Half the distance again, and everything changes. 12.7 million kilometres from the centre, we arrive at the event horizon. We opened this video with that number and used it to deflate an expectation. The horizon of the most massive object in our galaxy would fit inside the orbit of Mercury. At the time, that was an anticlimax, a way of saying that the centre of the Milky Way is smaller than you thought. It is going to mean something quite different in a moment. Let me first name the expectation almost everyone carries into this, because it is wrong, and the wrongness is instructive. The popular image of falling into a black hole is violence, being stretched, being pulled apart lengthwise into a thin stream of material, a process that has an actual technical nickname in the literature, spaghettification, which is a genuinely used term in serious papers, and which tells you something about how physicists talk when they think nobody is listening. The image is of a boundary that destroys you at the moment of crossing. For some black holes, that is exactly right. For this one, it is not, and the reason is arithmetic. Tidal force is not gravity. It is the difference in gravity across an object. Your head and your feet are at slightly different distances from the centre of the Earth, so they feel slightly different pulls, and the difference tries to stretch you. On Earth, that difference amounts to about 1 part in 3 million of your weight, which is why you have never noticed it. The strength of the effect scales as the mass divided by the cube of the distance. Now evaluate that at a black hole's horizon. The distance to the horizon is proportional to the mass. That is the Schwarzschild formula. So when you compute the tidal gradient at the horizon, you get mass divided by mass cubed, which is 1 over mass squared. The answer is 1 over mass squared. The tidal force at the horizon gets weaker as the black hole gets bigger, and it gets weaker fast. For a black hole of 10 solar masses, the kind that forms when a massive star collapses, the tidal stretch across a 2-metre human body at the horizon is on the order of 20 million times the Earth's surface gravity. You are torn apart long before you get there, not at the horizon, but thousands of kilometres outside it. For Sagittarius A star, 4.3 million solar masses, the same calculation gives a stretch of roughly 1/10,000th of a g. 1/10,000th of a g is the whole of it. That is less than the difference in apparent weight between lying down and standing up. It is a force you could not detect with your body under any circumstances. You would not feel it. There would be nothing to feel. So here is the general principle, and it is genuinely counterintuitive. The bigger the black hole, the gentler the crossing. Extremity and violence are not the same quantity. A supermassive black hole is not a more dangerous version of a stellar one. In the specific matter of surviving the horizon, it is a far safer one, because its horizon sits so far out that the field there is shallow, and now that number from the first part has turned over completely. It would fit inside the orbit of Mercury. When we said that at the start, it was a deflation. The centre of the galaxy is disappointingly compact, smaller than the picture in your head. Here it is the reason you are still alive. The horizon of Sagittarius A star is gentle, precisely because it is enormous in mass, which puts its horizon so far out from the centre that the field there has had space to flatten. Every step of the last four parts, the last stable orbit, the ergosphere, the photon sphere, the horizon itself, has taken place inside a sphere you could set down in our solar system without troubling Mercury. That is not an anticlimax anymore. It is the entire final act of this journey, and it happens in a volume small enough to hold in your head. Which brings us to the crossing itself, and I want to describe it exactly as it happens. Nothing happens. That is the whole of it. You are falling inward, and at some particular moment you pass through a surface 12.7 million kilometres from the centre, and there is no jolt. There is no wall. There is no membrane, no barrier, no flash, no sound, no shudder, no resistance. Your instruments read exactly what they read a second earlier. The tidal stretch across your body is 1/10,000th of a g, which is to say nothing. Space around you looks locally flat, because at that scale, with tides that gentle, it genuinely is. If you had a laboratory with you, you could run any experiment in physics you liked, measure the speed of light, weigh a proton, check the fine structure constant, time the decay of a muon, and every single result would come back exactly as it does on Earth. Not approximately. Exactly. Nothing has changed yet. We said that in the second part of this video, 26,900 light-years out, and it was a comfort. It was the reassuring news that the journey inward is uneventful for almost its entire length. It is still true. It is true here, at the horizon, and it is the most frightening sentence in this video, because you cannot tell. That is the thing. You cannot determine that you have crossed. There is no local experiment, no instrument, no observation available to you that would reveal it. The horizon has no local signature whatsoever. It is not a place in the sense that a coastline is a place. It is a global feature of the space-time, defined by which paths can eventually reach the outside universe and which cannot. And that is not a property you can measure from where you are standing. You could work out afterwards, from your trajectory and the mass, roughly when it must have happened. You could not have known at the time, and by the time you have done the calculation, the answer no longer affects anything you can do. The most consequential boundary in the known universe is one you cross without noticing. I find that harder to sit with than any amount of spaghettification, and I think the reason is this. A violent boundary is at least an event. It happens to you. There is a before and an after, and you are present for the transition. This is not that. This is a threshold that turns out to be the absence of a threshold. A line that exists entirely in the description written by somebody else, somewhere else, and not at all in your own experience of the place. So what actually did happen? Described from outside, the answer is that the roles of two coordinates exchanged. Out here, where the field is weak, the radial direction is a direction in space. You can go inward or outward or stay put. It is a choice, like left or right. Time is not like that. Time you move through in one direction at one rate, whether you want to or not. Tomorrow is not a place you can decline to visit. Inside the horizon, the radial coordinate takes on the character that time has out here. That is the actual content of you cannot escape. It is not that the gravity is too strong to climb out of, the way you might fail to climb out of a well. It is that outward has stopped being a direction. Decreasing radius is no longer optional in the same way that tomorrow is not optional. The centre of the black hole is not a place ahead of you that you are approaching. It is a moment in your future that you are approaching, and pointing your engines away from it does about as much good as pointing them away from next week. For anyone watching from home, the picture is completely different, and this is where the clock ladder we have been building finishes. At a radius 1% above the horizon, a hovering clock runs at about 10% of Earth's rate. A year there is a decade here. At 1 part in 1,000 above the horizon, the clock runs at about 3.2%. A year there is roughly 32 years here. There is a famous ratio from the film Interstellar, 1 hour on the surface corresponding to 7 years at home, which is a factor of about 61,000. To get that at Sagittarius A star by hovering, you would need to hold position about 3 meters above the event horizon. 3 meters, the height of a room. That is an idealized calculation. Actually maintaining that position would require an acceleration far beyond anything material could survive, and the film's own scenario relied on the black hole spinning at very nearly the maximum rate rather than on static hovering. But as an illustration of how steep the curve becomes, it is exact. And at the horizon itself, the ratio does not equal 0. This is worth getting right, because the popular phrasing, time stops at the event horizon, is misleading in a way that obscures what is actually strange. The formula involves the square root of 1 minus the Schwarzschild radius over the radius, and at the horizon that is the square root of 0, which is 0. But that formula describes a static observer, and there are no static observers at the horizon. Holding position there would require infinite proper acceleration, which means no object can do it, which means the quantity the formula computes does not correspond to anything. The ratio between a clock at the horizon and a clock at home is not 0. It is undefined. The question stops having an answer, and it stops having an answer because one of the two things being compared cannot exist. That distinction is going to matter enormously in a few minutes. Inside, there is not much time left. The maximum proper time available between crossing the horizon and reaching the centre for a black hole of this mass works out to pi times the gravitational constant times the mass, divided by the speed of light cubed. Run the numbers for 4.3 million solar masses and you get about 66 seconds. That works out to 1 minute and 6 seconds. It is the longest possible remaining lifespan of anything that crosses the horizon of Sagittarius A star, and the maximum is achieved by falling freely and doing nothing. Struggling shortens it. Firing engines shortens it. The way to have the most time left is to accept the fall completely, which is a physical result rather than a piece of philosophy, and I have never been able to decide how I feel about that. And what is at the end of those 66 seconds? General relativity says a singularity, a point where the curvature grows without bound, and the quantities in the equations become infinite. It says this clearly and unambiguously. It also, in the same breath, tells us not to believe it. Infinities in a physical theory are not usually discoveries. They are the standard signal that the theory has been pushed outside the range where it applies. Every physicist working on this treats the singularity as a placeholder for something we do not have the mathematics to describe, and getting that mathematics requires reconciling general relativity with quantum mechanics, which remains the largest unsolved problem in physics. There are candidates. A Planck-scale core of enormous but finite density, a bounce into some expanding region, various constructions from string theory in which the interior is not empty at all. None of them is established. All of them are motivated by real problems, particularly the black hole information paradox. The fact that Hawking's 1974 calculation suggests black holes radiate in a way that carries no memory of what fell in, which would violate one of the deepest principles in quantum mechanics. And in case you're wondering how long we have to wait for that radiation to tell us anything, Sagittarius, a star's Hawking temperature is around 1/10,000,000th of a millionth of a Kelvin. The cosmic microwave background is at 2.725 Kelvin. Our black hole is colder than the coldest thing in the sky by 14 orders of magnitude, which means it is absorbing far more than it emits and will keep growing for an almost unimaginable stretch of time. Evaporation cannot begin in earnest until the universe has expanded and cooled far below its current temperature, which will take something like 10 to the power of 100 years. So we have arrived. We have crossed every boundary this journey has to offer, and I want you to notice something about how we got here, because it is the thing the entire video has been arranged around. There have been 11 parts, a steady accumulation of losses, the dark sky, the stable planetary system, the closed orbit, the option of standing still, the reliability of vision, and finally the direction of the future itself. every single one of them real, every single one of them measured or derived from measurements, and the person falling through all of it never registered one. At the start of tonight, I asked a question and promised you the answer by the end. The question was where, on the journey from here to the centre of our galaxy, reality stops behaving the way it behaves in the room you're sitting in. We have made the trip. Let me lay out what we found. 26,900 light-years of travel produced no relativistic effect at all. At 1 light-year out, the clock still agreed to a part in a million. The first thing to change was the sky, which filled with stars until night ceased to exist, and the density that produced that sky made the whole neighbourhood dynamically unstable. At 120 astronomical units, in the light of a single star tracked for 30 years, Newtonian gravity finally gave the wrong answer. At 38 million kilometres, the stable orbit ended. Somewhere inside that, in the ergosphere, the option of remaining stationary ended. At 19 million kilometres, light began to travel in circles and vision stopped meaning what it had always meant. And at 12.7 million kilometres, the radial direction stopped being a direction and became a tense. That is a real list. Every item on it is measured, or derived from measurements, or both. Nothing on it is exaggerated. Now I want to ask a question about the list itself. Take any item, take the innermost stable circular orbit. What does unstable mean there? It means that an orbit at that radius, described in coordinates set up by an observer far away, does not return to itself under small perturbations. Take the ergosphere. What does cannot remain stationary mean? Stationary with respect to what? With respect to the distant stars. Take the photon sphere. Light orbits there. As seen by whom? As traced in the geometry as described from outside. Take the horizon. What is a horizon? It is the surface from which light cannot reach an observer on the outside. Every single one of those definitions contains someone else. Not one of them is a statement about what is happening at that location. Every one of them is a statement about the relationship between that location and somewhere far away. Remove the distant observer. Genuinely remove them, not just stop mentioning them. And each of those definitions stops referring to anything. There is nothing at the horizon that a local measurement could find, because the horizon is not a local fact. It is a fact about which paths eventually get out, and out is a word that only means something if there is an outside. So let us ask the other question. What does the falling observer measure? Their watch ticks at 1 second per second. It always did. There was never a moment on the entire journey when it did anything else, and there was never a moment when they could have detected that anything was unusual about it. Their ruler is a metre long, their kilogram is a kilogram, and the speed of a light in their laboratory is 299,792.458 kilometres per second. The number I asked you to hold on to 2 parts ago. Not approximately that. Exactly that. At 1 light-year out, at S2's pericenter, at the last stable orbit, inside the ergosphere, at the photon sphere, at the horizon. Inside the horizon, in the last 66 seconds, with the singularity in their future rather than in front of them, the speed of light in their own hands is the same value it has in every physics classroom on Earth. Every law of physics they can test holds. All of them. Everywhere. Including inside. So here is the answer to the question this video asked. Reality does not distort at the centre of the galaxy. Reality is exactly as consistent there as it is in the room you're sitting in. It is not thinner, not weaker, not stretched, not broken. There is no location in the Milky Way, or anywhere else, where physics is less true than it is here. A person falling towards Sagittarius A star is not travelling toward a region where the rules soften. They are in a perfectly ordinary place, obeying perfectly ordinary laws, right up to and past the point where we lose the ability to describe them. What distorts is not the place, and not the observer. What distorts is the relationship between the two. It is the exchange rate. It is the translation. It is the map connecting a clock there to a clock here. Both clocks are correct. Both people are correct. Neither of them has been damaged, deceived, or slowed down in any sense that has a local meaning. And yet there is no longer a single agreed account of how much time has passed, and eventually there is no longer any agreed account of anything at all, because the correspondence has come apart. Distortion, it turns out, is not a property of a location. It is a property of a comparison. And that is the part I did not want to give you until you had made the whole journey, because I think it lands differently once you have. Consider what you have always been able to take for granted. Two people can compare their watches and agree. Two people can agree on what happened first, on whether the door closed before or after the phone rang. Two people separated by an ocean, or by a continent, or by the whole width of the earth can synchronize and stay synchronized and build a civilization on that fact. Every appointment ever kept, every satellite ever tracked, every conversation ever had depends on it. Every human being who has ever lived has spent their entire life inside that agreement and, almost without exception, has never once had reason to notice it was there. It is not a law of nature. It is what a weak gravitational field permits. It is a courtesy extended by the local geometry, and this planet happens to sit in a place where the courtesy holds so precisely that we mistook it for the structure of existence itself. Move somewhere the field is not weak, and it is withdrawn. Not because either party's reality has failed, but because the thing that used to connect them no longer works. Let me make that concrete, because it is easy to hear as an abstraction and it is not one. Two people set their watches together and one of them goes to the last stable orbit around Sagittarius A star and stays a decade. When they come back, one is 10 years older and one is 14. Neither watch malfunctioned. Neither person did anything wrong. There is no correct answer to how much time passed because how much time passed was never a single quantity. It only looked like one because everyone who has ever asked the question has been standing more or less in the same place. Now push it further. The one who went in does not come back. They keep falling, past the ergosphere, past the photon sphere, past the horizon. And somewhere in there, the question of what they are doing right now stops having an answer at all. Not a difficult answer. Not an answer requiring better instruments. There is no fact of the matter about what is simultaneous with your present moment and theirs, because the geometry that used to connect the two has stopped supporting the connection. They are fine, you are fine. There is no longer a meanwhile. So, the closer you get to the centre of our galaxy, the more reality distorts. That is true, and now you know whose reality and relative to what. Your own stays perfectly intact the whole way down. What comes apart is the reality you share with the people you left behind, the common account, the single story you were both in. You do not lose physics. You lose the ability to remain in the same story as anyone else. Which brings me back to something from early in the night. At the centre of the galaxy, the sky never goes dark. I said that was a loss, and it is, and I think we can now see what kind of loss it belongs to. The darkness overhead on a clear night is not a fact about the universe. It is a fact about where you happen to be standing, in a thin, empty, quiet suburb where the stars are 5 light years apart. Move somewhere generous, and the night is simply gone. The agreement between your clock and everyone else's is the same kind of thing. It is not a fact about the universe. It is a fact about where you happen to be standing, in a place where space-time is so nearly flat that 2 watches will keep pace for a lifetime. Move somewhere the geometry is steep and that is gone too. Both of them are local privileges. Both of them feel like bedrock. Neither of them is. I find, at the end of this, that the conclusion is stranger and quieter than I expected, and also a good deal kinder. Because the fear underneath a video like this, the thing the title is playing on, is that somewhere out there, reality is fragile. That there are places where the universe stops working properly and things fall through, and it turns out that is not true, and it is not close to true. The universe is not fragile anywhere, not at the last stable orbit, not in the ergosphere, not at the horizon, not 66 seconds later. Only our agreement about it is fragile. That is the thing with the local dependence. That is what a strong field takes away. I should say, before we finish, that people have proposed other things sitting at the centre of our galaxy. A boson star, a gravis star, a dense ball of exotic particles, configurations that would have no horizon and no singularity. These are serious minority positions, argued in the literature by real physicists, and they are being squeezed hard by the data. S2's pericenter already forces 4.3 million solar masses inside a region smaller than our planetary system. The shadow matches the rotating black hole solution, and if there were a surface, infalling matter would settle onto it and glow, and it does not. They are not excluded with certainty. They are running out of room. And I should also say that the more colourful claims, that the centre of the galaxy sends energy waves at us, that we are being pulled in, that some alignment there matters for anything here, do not survive contact with a calculator. The gravitational pull of Sagittarius A star at this distance is about 10 to the minus 14 meters per second squared. The moon's influence on you exceeds it by an overwhelming margin. Nothing about it reaches us at all except its light, and even that has to fight through a trillion-fold curtain of dust, which leaves the one thing genuinely unresolved. We do not know what is inside, not in a modest way, in the strict sense that the equations return an answer their own authors do not believe, and the theory that would replace them does not exist yet. And there is a real argument that the answer is not merely unknown but permanently unavailable, because whatever is in there is causally disconnected from every observer who could ever ask. The information cannot reach us. It is not hidden. It is on the other side of a direction. So there is a fact of the matter at the centre of our galaxy, 26,900 light-years away, inside a sphere that would fit within Mercury's orbit, and it may be that no one will ever hold it. That is not a tragedy, and it is not a cliffhanger. It is just the shape of the thing. Somewhere out there tonight, S2 is drifting slowly through the far end of its orbit, running about 2 3/4 hours a year behind you, on its way back around for 2034. Your clock and its clock have already begun to disagree gently, by an amount nobody will ever notice, and the sky above you, wherever you are, is dark